Hello, my name is Scott Bryson, and I'm an applications engineer supporting Texas Instruments position sensing products. In this video, I will discuss how to use the TI Magnetic Sense Simulator to simulate linear motion using magnetic sensors. While linear motion can have multiple axes of freedom while moving the magnet, there are usually two main categories we might divide it into. The first is head-on travel. This motion typically has a sensor aligned to the polarization axis of the magnet, and the magnet traveling along that polarization axis. This works well with one-dimensional Hall effect sensors since all of the observed magnetic field should be in a single direction. The second mode is commonly referred to as slide-by motion. In this case, the magnet is offset in one direction somewhat with enough clearance to not strike the sensor. As the magnet travels by the sensor, this produces an input magnetic field, which is often used to track linear displacement. When linear motion is selected in the TI Magnetic Sense Simulator, there are a few key input fields used to define the travel of the magnet. These can be found by clicking to expand the magnet motion dropdown. The first input is the origin position. This will define the initial starting position of the magnet. Using the x-axis, y-axis, and z-axis inputs, it is possible to place the magnet anywhere in 3D space near the sensor. The second row within the origin position section will define the orientation of the magnet that it will keep throughout the simulated travel. Since the magnet is polarized in the z direction by default, it may be necessary to rotate about the x or y-axis to match the target alignment to the sensor. All rotations are carried out in XYZ order. The last set of fields in the magnet motion category will define the position of the magnet at the end of travel. Often two of the three fields will match the origin location values. By changing only one of the axes values, the motion will be constrained along a single Cartesian axis. It is possible to create more complex travel that varies using two or three axes as well. The last relevant configuration setting is found after selecting Sim Settings at the top of the input menu. This allows the user to define the incremental step size for the simulation. The tool will create as many evenly sized steps that can be divided from the total distance traveled by the magnet. To demonstrate, I'll walk through an example simulation using the tool. In this case, I will select linear for the function type and then will use a bar magnet for this example. For the sensor, I will pick a one-dimensional linear device that we can use to measure the Z component of the magnetic field. For this, I've chosen DRV5055. With all these inputs selected, we are ready to start configuring the simulation. I will leave the default magnetic material selected as neodymium type M35 magnet, and will also leave the default geometry as a 4mm cube. I can configure for a typical slide-by orientation by setting the start position to 10 mm in X, then the final position to minus 10 mm in X, and by rotating 90 degrees in Y. This would normally provide a Z-axis input that could be used in a slide-by configuration. To demonstrate that the magnet can travel with motion more complex than along a single axis, I will set the starting position to 15 mm. We see that when the simulation completes, that we can observe the travel of the magnet by clicking play, with the complete magnetic field information plotted on the right, but the Z input field is weak until the magnet gets close to the sensor. Now that we are familiar with the inputs for this type of motion, we can explore the two main types of motion already introduced. There are ready-made examples available to explore in the example reference designs. Let's go back to the start screen and select the head-on approach example. Head-on travel is simulated by forcing the magnet to travel along its axis of polarization. We could use a linear sensor already selected, or change our selection to DRV5032, which is a low-power Hall effect switch. We can make changes to the simulation, such as choosing a different device sensitivity or changing the package option of the device. We can also move the sensor position to increase the magnetic field strength observed by the sensor. Running the simulation will show us a plot for the expected range where the sensor will toggle when moving forwards as depicted in the animation, and the release point that would occur when withdrawing the magnet in the reverse direction. let's take a closer look at each of the plots. The magnetic field for this type of motion is inherently in a single direction when aligned with the sensor directly on the polarization axis of the magnet, and we can see that the magnetic field strength will exponentially increase as the magnet approaches the sensor. If we turn off the magnitude field in the plot, we can see that the field is entirely in the z direction. This type of motion is commonly used to define end of travel and limit detection functions. Commonly, this might be implemented using a Hall effect switch, such as a DRV5032AJ that we selected for this simulation. This device has a maximum operating threshold of 9.5 millitesla and a minimum release threshold of 3 millitesla. If we compare these thresholds to our plot, we would expect to see all corner cases for this device to operate and release within this window. Comparing to the output plot generated in the TI Magnetic Sense simulator, we can see that the expected transitions are displayed for both forward and reverse travel. Let's go back and try the other common motion type by selecting the slide by reference design. For this, we will look at the results of a disc-shaped magnet gliding above a linear Hall effect sensor from right to left. I'll leave the sensor type as the default 3D Hall effect sensor TMAG5273. We can see when running the animation that our magnet will glide by the sensor from the right to the left, and the magnetic field is more complex with components in multiple axes. This type of input field is commonly used to perform linear encoding functions. Whether oriented with the magnetic pole directed toward the sensor or rotated 90 degrees with the pole oriented along the path of travel, we will expect to see a similar profile of the magnetic field. For one direction, the input will typically look similar to a Gaussian bell curve, while the second axis will demonstrate a somewhat S-shaped contour. In the case of a one-dimensional sensor, it would be desirable to use the linear section on the S-shaped contour we currently see in the X direction. Here, the maximum sensing range is limited to the region between the peak values, which is most linear around the center of the magnet. In fact, the size of this linear region often scales with the length of the magnet. Since increasing the size of the magnet may not always be a practical option, it is necessary to create a sensor array to expand the range using one-dimensional sensors. However, there is still more magnetic field data that could be used by a three-dimensional sensor to expand the sensing range. When using the full magnetic field, angle calculations can be used to determine a much wider stroke length. The challenge here, though, is that an unadjusted arctangent measurement will be quite nonlinear, so this method often requires characterization to reach the best overall accuracy. To learn more about the TI Magnetic Sense simulator, please visit the tool page and check out the user's guide. You can also learn more about sensing linear motion by reading the application notes or by exploring other content on TI.com by following the link shown here. To get started on your linear motion simulation, please visit www.ti.com/TIMSS.